In the coming sections, we will learn about the constitutive analysis, which deals with the effect of strain rate and temperature on flow properties. Flow stress can be considered as a function of strain, that is epsilon, strain rate, that is epsilon dot, the working temperature or capital T, and the microstructure or the composition of the material. Now in the previous sections, we have already learned that the variation of flow stress sigma with strain epsilon is given by a power law equation, which is sigma is equal to k into epsilon to the power of n, which is generally termed as the Holomon equation and which is valid within the region of strain hardening. In this equation, K is the strength coefficient and N is the strain hardening exponent of the material. Now, the general relationship between the flow stress sigma and the strain rate epsilon dot at a constant strain and temperature is expressed as sigma is equal to C into epsilon dot to the power m at a given strain and temperature, where C is a constant term and m is called the strain rate sensitivity of the material. So, from this equation, it is clear that the flow stress sigma will increase with the increase of strain rate or epsilon dot. So firstly, from this equation, we can learn that the flow stress sigma will increase with the increase in strain rate or epsilon dot at a given value of strain and temperature. This is revealed from this particular figure, which shows the variation of yield strength with strain rate. Here we can see that the yield strength of a material will increase with the increase in strain rate at different given values of temperatures. Next, secondly, if we take logarithm on both sides of this equation, we get another equation where we can see that the slope in between the log of sigma and the log of epsilon dot actually gives the value of m or the strain rate sensitivity of a material. So, m is determined by measuring the change in flow stress brought about by a change in strain rate at a constant strain and temperature. Here in this equation, we can see that m is equal to the derivative of log of sigma by log of epsilon dot at a given value of strain and temperature, which is represented by epsilon dot by sigma into the derivative of sigma by epsilon dot, which is ultimately represented by the log of sigma 2 by sigma 1, that is the change in flow stress value, by the log of epsilon dot 2 by epsilon dot 1, that is the change in strain rate value. Thus, if we can draw a plot of log of sigma by log of epsilon dot, from the slope of the lines we can get the value of m, or the strain rate sensitivity. As in the earlier sections, we have learned about the engineering and true stress and strain values. Now, the strain rate can also be engineering and true. Firstly, the engineering strain rate. The engineering strain rate, which is denoted by E dot, is equal to dE by dt, that is the change in engineering strain with respect to time. Now, the engineering strain E is equal to L minus L naught by L naught, where L naught is the initial length of the specimen and L is the actual or the instantaneous length of the specimen. Now, since L naught or the initial length of the specimen is a constant, so this equation is represented as 1 by L naught into dl by dt, where this change in length is represented by dl. Now, this term dl by dt, that is the change in length with respect to time, is given by v, that is the cross-set velocity of the testing equipment. So, the engineering strain rate becomes v by L naught, where v is the cross-set velocity and L naught is the initial length of the specimen. Next is the true strain rate. Now, true strain rate is denoted by epsilon dot, which is equal to d epsilon by dt, that is the change in true strain with respect to time. Now, the true strain is equal to log of L by L naught, as we have learned in the earlier section. So, this equation is represented by 1 by L into dl by dt. So, once again, substituting dl by dt with the cross-set velocity v, we get the value of true strain rate, that is epsilon dot is equal to v by L, where v is the cross-set velocity of the testing equipment and L is the actual or the instantaneous length of the specimen. Now, a relationship can be drawn between the engineering and the true strain rate. We start with the true strain rate, that is epsilon dot, which is equal to v by L. Now, we substitute the value of v from this first equation, which gives us the v is equal to L naught into dE by dt. Now, from the earlier sections, we have learned that L naught by L gives us the value which is represented by 1 by 1 plus E, where E is the engineering strain. So, this equation is represented by this particular term, that is 1 by 1 plus E into dE by dt, and which ultimately gives the value of this term, that is the E dot by 1 plus E, where E dot is the engineering strain rate and E is the engineering strain, which ultimately gives the value of the true strain rate. So we can see that the true strain rate epsilon dot is represented in terms of the engineering strain rate E dot, that is equal to E dot by 1 plus E. Now, to maintain a constant true strain rate, that is epsilon dot, the deformation or crosshead velocity must increase with time in proportion to the increase in specimen length, that is L naught. Now this is revealed from this particular equation, where we can see that the crosshead velocity V should be equal to epsilon dot into L naught into exponential of strain rate, that is epsilon dot into T. So where the epsilon dot is a true strain rate that has to be maintained, and L naught is the initial length of the specimen. So to maintain a particular true strain rate value, we have to vary the crosshead velocity with respect to time as per this particular equation. After studying about the effect of strain rate on flow properties, now we study about the influence of temperature on the flow stress. The temperature dependence of the flow stress sigma at a constant value of strain, that is epsilon, and strain rate, that is epsilon dot, generally can be represented by this particular equation, which gives us sigma is equal to C2 into exponential of Q by RT at given values of strain and strain rate, where C2 is a constant term once again, Q is the activation energy for plastic flow, and R is a universal gas constant. So from this equation, it is evident that the flow stress or the sigma value will decrease with the increase in temperature or capital T. Now this particular fact is revealed from the given figures. The first figure gives us the effect of temperature on the stress strain curves, where we can see that with the increase of working temperature, the stress strain curve is changing, or more precisely, the strength is decreasing while the ductility is increasing. Now, the effect of temperature separately on the strength and ductility is given by the next two figures. The second figure gives us the variation of yield strength with temperature, where we can see that for different materials the yield strength is decreasing with the increase in temperature. And the next figure represents the effect of temperature on the ductility of the material, which is represented by the percentage reduction in area. Here we can see that for the same set of materials, the ductility is increasing with the increase of temperature. So the effect of temperature separately on the strength and ductility of a material can be revealed from these figures. Now let us study about the combined effect of strain rate and temperature on flow properties. Here we can see the true stress versus true strain curves, or the flow curves, which were obtained from the compression test performed at 4 different strain rates, that is 0.001, 0.01, 0.1 and 1 per second, and 5 different temperatures, that is 300, 350, 400, 450 and 500 degrees centigrade. So these are the flow curves which were obtained under the different values of strain rates and temperatures. From these flow curves, two major observations were derived. The first observation is, at the onset of plastic deformation, the flow stress sigma increases rapidly at a decreasing rate with increase in epsilon, that is strain, up to a maximum stress, that is sigma p, which is called the peak flow stress. Beyond the peak strain, which is denoted by epsilon p, that is the strain to reach this maximum stress, the sigma either decreases, as we see in this flow curve, or it attains saturation, as we see in this particular flow curve. The former behavior is observed when the softening rate is higher than the work hardening rate, while the later one occurs when the softening rate is equal to the work hardening rate. Then, as we see that we get the different values of peak flow stress for different conditions of strain rates and temperatures, we can observe that the peak flow stress increases with increase in strain rate and decrease in deformation temperature. So this is our second observation. Thus, we can get an idea about the combined effect of strain rate and temperature on the flow stress or the peak flow stress values. In the earlier section, we have learned that the flow stress will vary with variation in strain rate and deformation temperatures. Now this flow stress may be computationally modeled by means of constitutive analysis, and then the flow stress may be predicted in terms of strain rate and temperatures through these different constitutive models. In this section, we will discuss about the different constitutive models which are available. First, we start with the Arrhenius equation of heat activation, which says the strain rate denoted by epsilon dot is equal to A, which is a constant, into F sigma, which is a function of sigma, into exponential of minus Q by RT, where Q is the activation energy of deformation, R is a universal gas constant, and T is the working temperature. Now, the different expressions which are generally considered for this F sigma are as follows. Firstly, the F sigma may be represented as a power equation, that is sigma to the power of n1. In this case, the strain rate epsilon dot becomes this particular expression, where the constant A becomes A1 in this case. When we take logarithm on both sides of this equation, we get the following expression, where we can see that if we draw the plots of log of strain rate versus log of sigma, the slope gives the value of n1. Here, this particular power law equation breaks down at high stress values, which is a disadvantage for this particular constitutive model. The second function of sigma which may be considered is an exponential function, that is exponential of beta into sigma. When we take this particular function of sigma, then the strain rate becomes this particular expression, where the constant term A becomes A2 in this case. Similar to the earlier one, when we take logarithm on both sides of this equation, then we get this particular equation, and here again we see if we draw plots of log of strain rate versus sigma, the slope gives us the value of beta. Now here the constraint is this particular exponential equation breaks down at low stress values. The third one, which is the most commonly used, is the function of sigma, that is F sigma, is represented by sine of hyperbolic function, that is sine of hyperbolic alpha into sigma to the power of n. So in this case, the Arrhenius equation becomes the strain rate is equal to A3 sine of hyperbolic alpha sigma to the power of n into exponential of minus Q by RT. Here the constant A becomes A3 in this case, and alpha is the stress multiplier, which we will learn about in the later section. So once again, when we take logarithm on both sides of this equation, we get this particular expression. When we draw the plots of log of strain rate versus log of sine of hyperbolic alpha sigma, the slope gives the value of n and the intercept gives the value of A3, because this expression gives a straight line equation. So the advantage of this particular constitutive model or this particular function of sigma is, over a wide range of stress values, this hyperbolic sine law is found to be most suitable for modeling the high temperature deformation behavior. And this is the reason why this particular constitutive model is generally and commonly used. At this point, it is pertinent to mention that for each flow curve, in place of the flow stress, we are actually considering the peak flow stress or sigma p values. Now in this section, we will discuss about the stress multiplier alpha and its evaluation. The stress multiplier denoted by alpha may be optimized or approximated by two different methodologies. Let us first consider the first methodology. If we draw the plots of log of strain rate versus the peak flow stress sigma p at different given values of temperatures, we actually get the different sets of points, and the straight lines may be fit through these different sets of points corresponding to the different temperatures. From the previous section, we have learned that the average value of the slopes from these straight lines will give us the value of beta with respect to the second constitutive model. Again, if we draw the plots of log of strain rate versus the log of peak flow stress or sigma p for different values of temperatures, we once again get the different sets of straight lines which are fit through the different sets of points, and the average slope value gives us the value of n1 with respect to the first constitutive model. Now the stress multiplier or alpha is approximated to this beta by n1, which means that the stress multiplier alpha may be evaluated if we draw these two sets of plots. The first one, log of strain rate versus the peak flow stress sigma p, and the second one is the log of strain rate versus log of peak flow stress or sigma p. In the second methodology to evaluate alpha, we are actually generating the plots of log of strain rate versus log of sine of hyperbolic alpha sigma p corresponding to the different temperatures once again. So again we get the different sets of points through which the straight lines may be fit into. Now the stress multiplier alpha may be optimized to generate these plots as much linear and parallel as possible, that is, the coefficient of determination, that is r square, should be nearest to 1. So these are the methodologies through which the stress multiplier alpha may be optimized or approximated. In the next stage, we have to evaluate the value of activation energy or Q. Now the activation energy for deformation is represented by this expression, which is equal to R into the derivative of log of strain rate by 1 by T at a given value of sine of hyperbolic alpha sigma. Now this particular derivative may be resolved into two components. The first component here is denoted by n, which is the derivative of log of strain rate by log of sine of hyperbolic alpha sigma at a given value of temperature. So this derivative may be evaluated if we draw the plots of log of strain rate versus log of sine of hyperbolic alpha sigma p. Once again we get the different sets of points for different temperature values, and the straight lines may be fit into where the average value of the slopes give us the value of this derivative or n. The second component is denoted by S, which is the derivative of log of sine of hyperbolic alpha sigma by 1 by T at a given value of strain rate. So this derivative may be evaluated if we draw the plots of log of sine of hyperbolic alpha sigma p with respect to 1 by T at the given values of strain rates. So once again we get the different sets of points. In this case, these are the 4 sets of points for 4 given values of strain rates, and through which the straight lines may be fit into. So the average slope value may give us the value of this derivative or S. So once we draw these two sets of plots and evaluate the average slope values, we can evaluate the value of this n and S, that is these two derivative values. Thus the activation energy denoted by Q of the material is equal to R into N into S, where R is a universal gas constant and N and S can be evaluated from the average slope values from these plots. The unit of the activation energy is kilojoule per mole. So the activation energy denoted by Q of the material may be evaluated by this particular methodology. At this point of time, we introduce a new parameter called the Zener-Holomon parameter or Z. In this expression, we see the Zener-Holomon parameter denoted by Z is equal to epsilon dot, which is the strain rate, into exponential of Q by RT, where Q is the activation energy for deformation, R is a universal gas constant, and T is the working temperature. Now considering the different constitutive models, when we substitute the value of the strain rate, that is epsilon dot, we get the different values of the Zener-Holomon parameter or Z. For example, in the first case, for the power law equation, when we substitute the value of strain rate, we get Z is equal to A1 into sigma to the power of N1. In the second case, for the exponential equation, when we substitute the strain rate, we get Z is equal to A2 into exponential of beta into sigma. And in the third case, that is for the sign of hyperbolic law, when we substitute the value of strain rate, we get Z is equal to A3 into sine of hyperbolic alpha sigma to the power of n. Now we know that this dynamic recrystallization is actually the reason of flow softening. Dynamic recrystallization is favored at low Z values, that is at low strain rates and high deformation temperatures. It is evident from this equation that the Zener-Holomon parameter Z will decrease with the decrease in strain rate and increase in deformation temperature, or in other words, the Z values will be lower with lower values of strain rates and higher values of temperatures. So for this lower values of Z, the dynamic recrystallization will be favored, where the flow softening will occur. In case of the present experimental results, here the log of Z values have been tabulated with respect to the different strain rate and temperature values. Here we see the cases of low strain rates and higher deformation temperatures have been highlighted, where the dynamic recrystallization will be favored. So this is one significance to evaluate the Zener-Holomon parameter Z, that is for the lower values of Z, the dynamic recrystallization or flow softening will be favored. The major significance of Zener-Holomon parameter Z lies in the evaluation of the constitutive constants, that is A3 and n. If we take logarithm on both sides of the equation of Z, we get the equation of log of Z is equal to log of A3 plus n into log of sine of hyperbolic alpha sigma p. Now this equation is a straight line equation where the slope gives the value of n and the intercept gives the value of A3. Here in this figure we can see that if we draw the plots of log of Z versus log of sine of hyperbolic alpha sigma p, we get a series of points through which a single straight line may be fit into with the highest possible r square value. Now the slope of this straight line gives the value of n, while the intercept gives the value of A3. Thus the constitutive constants of A3 and N may be evaluated by plotting the log of Z versus log of sine of hyperbolic alpha sigma p values. Thus, the significance of Zener-Holomon parameter or Z may be summarized as follows. The peak stress sigma p and Z values, both of them increase with increase in strain rate and decrease in deformation temperature. A single straight line can be drawn through the experimental data between log of Z and log of sine of hyperbolic alpha sigma p using the selected value of alpha. The values of constants, that is A3 and N, may be evaluated from the intercept and slope of the straight line respectively. So, these are the major significances of Zener-Holomon parameter or Z. We have now reached at a stage where we can evaluate and predict the value of flow stress in terms of the strain rate and deformation temperature. By this stage, we have already optimized the value of stress multiplier alpha. We have evaluated the value of activation energy for deformation, that is Q of the material, and we have evaluated the constitutive constants of A3 and N. Now, when we substitute the values of all these parameters in the main constitutive equation of the material, we get this expression in terms of the strain rate epsilon dot and the expression for Zener-Holomon parameter or Z. Now, from the main constitutive equation, if we bring the peak flow stress sigma p in the left hand side, it can be represented by all other parameters. Here in this equation, we can substitute the values of stress multiplier alpha, the activation energy for deformation, that is Q, and the constitutive constants of A and N. So finally we get the expression for peak flow stress in terms of only the strain rate, that is epsilon dot, and deformation temperature, that is T. So for different values of strain rate and temperature, if we substitute the values of epsilon dot and T, we can evaluate and predict the values of peak flow stress or sigma p. Thus, the flow stress can be modeled and predicted in terms of the strain rate and temperature by means of the constitutive analysis.